Hey guys, today we're going to go over Chapter 8, Lecture 19, Learning Objectives 6 and 7. We're going to be looking at our formal charges and we're going to be looking at resonance structures. So just as a reminder, we're looking at Lewis structures. So we have a structure that has lone pair electrons, and bonds. And the lone pair electrons are electrons that are just on one atom. So we call these non-bonding electrons. And then we have our bonds. So these are shared electrons. And they come in three varieties. Single, we have one pair of shared electrons. Double, so two pair. And then triple, three pairs. Okay, so with our lone pair electrons, these are on just one atom. The bonds, however, are going to be shared between two atoms. So it's important when we're talking about the idea of formal charges to understand the difference between these lone pair electrons and these shared electrons. So when we have a structure such as NH3, we have, actually, these right here are our unshared electrons, so those non-bonding. And then these right here are the shared electrons. So if we've got an atom that is not sharing electrons, then it's going to feel both of the negative charges from both electrons. While if we have a shared pair of electrons between two atoms, then it's kind of like each atom feels half of that electron's negative charge, giving it only really the feel of having one electron, though both are participating in both atoms' octets. So this brings us to the idea of a formal charge. So let's actually kind of compare it real quick with things we've looked at already. Oxidation numbers. We're going to look at our formal charges. And we're going to compare this to the partial charges we looked at just recently. So remember our oxidation numbers. That's when we were looking at redox reactions. These are going to be the charge an atom has if you assume all the bonds are completely ionic. So we have that transfer of an electron. So this is kind of a overstated electronegativity. Where we have, instead of just electrons being pulled towards a more electronegative atom, we have electrons being shifted from one atom to the other, the one that has the greater electronegativity. So there's going to be an assumed electron transfer from the atom that is less electronegative to the atom that is more electronegative, which we know is not true in covalent substances, but it's a really good bookkeeping method when we're thinking about our redox reactions. So these are free redox reactions. Then we have our formal charges, what we're looking at today, where this is going to be assuming that we have a purely covalent species. So this is a charge an atom has if you assume the structure is purely covalent, meaning that all electrons are going to be shared equally. So in this case, we are going to ignore electronegativity. And this is going to help us determine if we have a good structure. So it's used to determine structure stability. Okay. And then what we've looked at already, but we're going to revisit right now, are the idea of partial charges. Partial charges actually takes a good approximation of electronegativity. So it is saying that, okay, we have covalent bonds, but we do not have pure covalent bonds. We can have covalent bonds that have some ionicity to it, as in one atom can pull electron density more than another within a bond. So this is taking into account electronegativity. So here atoms are covalently bonded, or covalently bonded, but there is a pull on electrons by the more electronegative atom in a bond. And if the difference in electronegativity is great enough, we will produce a polar covalent bond, where we have a shift where the electrons are not perfectly shared between the two atoms, but there's a shift. So this is going to factor in electronegativity fairly well. So it'd be a good approximation. And this is going to help us determine, we use these to determine physical properties. Of a molecule. So is it going to have a high boiling point, a low boiling point, high melting, low melting, those type of things can be determined by looking at partial charges. Okay, so let's go into the idea of a formal charge a little bit more. So our formal charge here, again, we assume everything is perfectly covalent, so there's an equal sharing of electrons. And basically, we want to assume that formal charges are kind of bad things to have. So formal charges cause instability. So we want to minimize those whenever possible. So to determine our formal charge, this is going to be equal to the number of valence electrons, and this is for an atom. So we take the number of valence electrons the atom has, minus number of bonds, of the atom and the number of non-bonding electrons on atom. Okay, so this we're going to get from the periodic table. So for instance, if we're in group 14, it has 4 valence electrons, 15, 5 valence electrons, 16, 6, so on and so forth. And like I said, you have to do this for each atom within the structure. Our number of bonds and number of non-bonding electrons we're going to get from the Lewis structure. And if we have a single bond, for each single bond, that equals 1 bond. For each double bond, that equals 2 bonds. And for each triple bond, that equals 3 bonds. And then our number of non-bonding electrons, 1 electron equals 1, 2 electrons, 2, so on and so forth. Pretty easy. Let's try an example. Let's take ClO minus. So we're going to draw the Lewis structure for this and then figure out our formal charges on each of the species. So if we have chlorine and oxygen, those together are going to have 14 valence electrons. We're going to put them together looking like this. So there's 2 of our electrons, 4, 6, 8, 10, 12, 14. So that's our total electrons. It has a charge, so it's going to look like this. And that is our Lewis structure. After we've drawn our Lewis structure, we can then do the formal charge of chlorine and the formal charge of oxygen. So chlorine has 7 valence electrons because it is in group 17. It has 1 bond and it has 6 non-bonding electrons, giving us a formal charge of 0 for chlorine. For oxygen, we have 6 valence electrons, 1 bond, and 6 non-bonding electrons. Excuse me, giving us a -1 formal charge. As you notice, hopefully, when we sum together our formal charges, we get a -1, and the sum of the formal charges will equal the charge of the molecule, which would be 0, or polyatomic ion, which in this case is -1. Okay, let's move on to the idea of resonance, which also tells us information about the stability of a molecule. So let's think about ozone, for instance. O3. O3 has the following following Lewis structure, like so. If we were to draw formal charges for this, let's say, okay, this pink one is 1. So for a formal charge of pink oxygen, this is 6 minus 2 minus 4, which gives us 0. Our formal charge for blue oxygen is 6 minus 3 minus 2, which is plus 1. And our formal charge for purple oxygen is 6 minus 1 minus 6, which is -1. Sum all these together. We get a 0, which is what we have here. So perfect. Now, this structure I've written like this. Another option for this structure is this right here, which looks identical to the other one, just flipped. So we would say that these two structures, the one I drew initially and then the second one that I drew, are two ways that we could describe our O3. So ozone can be described in either way. Here we have a single bond, then a double bond. Here we have a double bond, then a single bond. If you actually look at the bond lengths in ozone using advanced techniques, you find that these bonds are actually equivalent. And though you may not know this, if you have a double bond, it is going to be shorter than a single bond. We'll talk about that shortly. But if you have two bonds, one's single, one's double, but they're actually showing up as the same they're showing up as the same bond length, that means we don't have different bonds. We have the same bond. So we can actually describe ozone like this. Where that extra pair of electrons is floating between the two bonds. So this is a 1.5, 1.5 instead of a 1 and a 2. So the actual structure of ozone is a structure between the two resonance structures we drew above. So these two above are called resonance structures, and then the one that takes into account all of the things that are going on here is called a resonance hybrid. Okay, so this is going to be an average of the two structures. And we average them because they are equivalent in stability. Both of them are the same stability. And then with this one, we have a negative, positive, positive, negative. In our resonance hybrid, we have a negative 1/2, negative 1/2, and a positive. So we've distributed our charge more. So this is charge distribution, which is something we want to do. We don't want to localize charge anywhere. So this ability to have these two resonance structures is going to stabilize our O3. So we would say that resonance in a molecule is stabilizing. That's because we delocalize charge. So we're going to distribute charge. So instead of it all being in one area, we've pushed it throughout the entire molecule. So we've dissipated that charge in a way. So when we draw a Lewis structure, you always want to draw all the stable resonance structures available. So in this case, we have two Lewis structures, and they're both going to be equivalent in stability. And you can always tell if something's equivalent to stability by looking at your formal charges. If you want to minimize formal charges, so a stable Lewis structure minimizes formal charges, gives octets to all molecules, or sorry, all atoms, in the molecule. And of course, exceptions exist. For instance, hydrogen, you never want to have an octet for hydrogen. That just would not be very happy for hydrogen with its 1s electron. And if you have to have a formal charge, you want to put formal charges on atoms that make sense. So if you must have a formal charge, place negative formal charges on more electronegative atoms, positive formal charges on more electropositive atoms. Okay? So when we have a resonance structure, or when we have resonance structures, you have resonance structures when you have two or more stable Lewis structures for a molecule, a particular molecule. Anytime you have resonance structures, you have delocalization of electrons. And specifically, it's delocalization of pi electrons. We'll talk more about that in chapter 9, but I just want you to think about that, or have that kind of in the back of your mind. Um, but think about another example. We can look at the acetate atom, or molecule. So here, we draw our Lewis structure. It looks like this. Like so. Or like this. And these would be our two resonance structures, or our resonance hybrid, where we take the delocalized electron, like so, and we put a negative charge in there. Or you could write it as that. So these are our resonance hybrids for acetate. So when we're trying to draw a Lewis structure, this is what we're going to do. We are never going, so we're going to move lone pair electrons. Or electrons in multiple bonds. We are not going to break single bond electrons. So we're not going to break a bond, an actual single bond. So we're not going to stop atoms from being bonded to each other. So do not move single bond electrons. Only electrons that are in double, so one of the pairs of electrons within double, or two of the pairs of electrons within a triple. We're not going to break the octet for any elements below period 3. So expand the octet more than 8. For elements below period 3. Or remove an octet from an atom that already has one. Again, for elements below period 3. Actually, that's not even. So have fewer than 8 electrons. So if we are below period 3, we want to make sure that we don't have more than 8 electrons. That's what we're saying here. Or if we have an atom that already has an octet, do not remove electrons to cause it to have not an octet anymore. Okay, and determine formal charges on all atoms to let's do calculate. That sounds funny. Calculate formal charges on all atoms to determine the most stable structure or structures. One of the most stable structures we have because of resonance is benzene. Benzene, if you were to write out its Lewis structure, would look like this. So it looks like alternating one single and double bonds, where a carbon-carbon single bond is 1.54 angstroms, a carbon-carbon double bond is 1.34 angstroms, but the bonds in benzene are all 1.40 angstroms, meaning that they are somewhere between the two. So we'd say that all the bonds in benzene are actually 1/2 bonds. So our bonds in benzene equal 1.5, not alternating one single and double. So our resonance hybrid looks like this. A lot of times you'll actually see it look drawn like this, just to simplify, so getting rid of all of the atoms. But this is a perfect example of a structure that is very stable because of resonance. So it has two different resonance forms, and then the delocalization, these three pairs of electrons we see here, are delocalized amongst 6 atoms. So that really stabilizes that structure. Okay, let's try an example. I'll be done with this video. So we want the two resonance structures for hydrogen carbonate ion. So if we draw this, we would get, this could be one of our examples of a resonance structure. I'm going to show you how we are actually going to move these electrons. So we're going to move this pair right here. It's going to go here, which will cause that carbon to have more than octet. So we need to move these like so. And what we get that pair of electrons going right there, that pair of electrons going there, and while we formerly had a negative charge here, we get a negative charge here. So if we were to draw the hybrid, it would look like this right here. Okay, that is everything for this video. I will see you guys in the next one.